Good afternoon, everyone. How are you today? Good. Right. Okay. Let's have a quick recap about what we have learned last week. Last week we start to learn single-phase systems, right? And we need to know the density of the solid, density of liquid, and density of the gas. Especially density of gas is related to temperature and the pressure. Okay, and then we know the ideal gas equational state, which is PV equal to nRT. So that's what we have learned, and especially I think you have learned this before when you are in high school. So and then we go through that very quickly. So and after that we we introduce standard temperature and pressure. So standard temperature, you know, the standard temperature is 0 Kelvin, right? Standard pressure is 1 atm. So that's what you have learned. And this topic related to, are we going to use gas constant to do the calculation or not? And we deliver one example for you to let you know why we don't want to use gas constant. This is related to the for example, this case, right? If you want to measure the volumetric flow rate in this process, and this process is under high pressure and high temperature, it is no way for you to have equipment to put into this reactor or to put into this process to measure the flow rate. Okay, so we need to deliver this gas or this liquid to another space, another place, in which we define this system or this place is with a standard condition, which is 0 Kelvin and 1 atm. And at this moment, at that moment, we can use the conventional meters, for example, rotameter or pressure gauge, to measure the pressure and temperature. So that if you get the right answer and you use P1 V1 equal to P1 V1 divided by T1 equal to P2 V2 divided by T2, then you can get an answer of the volumetric flow rate, for example, or mass flow rate. Okay, this is another example. And after that, because the one we just discussed above is only we dealing with single gas, single type of gas. For example, you use nitrogen, you use oxygen. And then for the section 5.2c, we were talking about the ideal gas mixtures. For example, you have mixture of the argon and the nitrogen. So and how are you going to make the differences between PV equal to nRT using different species? So we introduce you Dalton's law, right? Dalton's law, and this is what you need to remember: is the partial pressure of partial pressure for a species A will equal to the molar fraction of A times total pressure. This is what we call Dalton's law, right? Okay, then Amagat's law is that the value of the pure species A will equal to the molar fraction of the species A times the total volume. So this is called Amagat's law. And I want to let you know that in chapter 6 we will use Dalton's law a lot. So please, you need to remember the partial pressure of species A equal to the molar fractions of species A times total pressure. Okay. And also, we also give you an example last week to let you understand why Dalton's law and Amagat's law is important in the mass balance equal to output, input equal to output, because when we're dealing with the flow, which is gas or liquid, this is the one of the examples showing you that acetone's partial pressure, if acetone's partial pressure is 501 millimeter mercury, and if you know the total pressure, you can find out the molar fraction of the acetone. This is one of the specifications you can use to do the mass balance, which is input equal to output. Okay. Right. So and in the end we introduce heat pump. Heat pump is a energy exchange device, and then is very popular to use now. For example, like the dehumidifier, you use a heat pump. You use the principle of this is the principle of the dehumidifier. And I just introduced you nowadays. They are a very popular washing machine. You can have a dryer in a washing machine, and they use the heat pump technology in the washing machine. So you can wash your clothes, and right after you dry your clothes. So you don't need to worry whether it's a raining day. You cannot dry your clothes very well, or you are busy. You cannot dry your clothes after you wash your clothes. So you just put it in and it's done. Okay. Right. So and then the end of the last lecture last week, we start to introduce non-ideal gas, right? Non-ideal gas, and this is one of the examples is that there's no ideal gas at all. Okay, so it's important that you understand why there's no non-ideal gas, and that it's important terms you need to know is called critical temperature and critical pressure. Before we introduce you the equations of the non-ideal gases. Okay? So we start from here today. Right. So what is critical temperature and critical pressure? So ideal gas, normally we think, when we talk about ideal gas, it need to be under some conditions, right? For example, high temperature. High temperature is higher than 0 Celsius. And we're talking about low pressure, which is less than 1 atm. Under this condition, we can regard the gas is an ideal gas. But it's not, this is roughly definition. This is not exactly, okay? So how well or poorly gas equation of the state fit PVT data? So when we talk about gas, we always talk about pressure, volume, and temperature. Okay? For a species often depends on the volume of the system, temperature, and pressure related to the two physical properties of the species. That's why we're going to introduce you. One is called critical pressure, temperature, and critical pressure. We use this symbol, T sub C and P sub C. T sub C stands for critical, okay? P, of course, P here is represent pressure, okay? C here is represent the critical. Okay, and how are you going to find out the critical temperature and pressure for water? Or how are you going to find out critical temperature or critical pressure for carbon dioxide? You can find out this in the textbook, in our textbook table B1 here. Okay, you can just type critical temperature and critical pressure of the methane, and Google will come out to tell you this. So this is one of the examples. This is some kind of substance, or you can call solvent, and this is related to critical temperature and critical pressure. I actually want to show you some example. For example, carbon dioxide. The critical temperature is 31.1 Celsius, which is very low. And critical pressure is 73.8. Okay, this is high pressure. Okay, I don't want you to remember this number, but you need to know roughly what in the range. Okay, because carbon dioxide, you know, its temperature is quite low, but pressure is about 70. You know, bar is relatively to ATM, so it's about 74. You know, 72. Sorry, 73 or 70 ATM, something like this. This is one of the important gas you need to know. Another important thing is water. The water critical temperature is 374.2 Celsius, and then the critical pressure is very high. It's about 220.5 bar. when I was a PhD student, I play water using I use supercritical water to do some experiment. Supercritical water is that the temperature need to be more than this. Temperature need to be more than this, and pressure need to be higher than this. So when I do this, my experiment, I'm a little bit worried when it's going to explode, right? This is very high pressure and high temperature. It's not. You need to operate your device or equipment with caution. You need to do it very carefully. So that's why what we call that is supercritical fluid. Okay, if the temperature and pressure above the critical temperature and above the critical pressure, that kind of fluid we call supercritical fluids. So let me show you what is supercritical fluids and what is critical temperature and critical pressure. Okay, this is a table showing you that this one, if we have a container with a piston here, and the piston, inside the container is full of the vapor, which is H2O in gas phase. So there's no liquid, there's no solid. And then let's say that the temperature is T1 and the pressure is P. Okay? Temperature T1 and pressure is P. So if we press the piston down, what happened? And we keep the temperature as a constant, then what happened? Pressure will increase, right? Pressure will increase. Am I right? Use your imagination. If I press the piston down, I will keep the temperature as a constant. So in this environment, the temperature is still T1, but the pressure will be increased, right? And at least, so you keep on pushing. So eventually, you will find out a kind of liquid come out. So as I told you that this environment, there's no liquid, only gas. But when you push very hard, you'll find out the first drop of the H2O, L stands for liquid, appeared. So at this moment, let's say if the temperature is T1 is 100, and if you push this down at condensation pressure, which is 1 atm, okay, and you will find out the first drop of the water come out. Okay? At this moment, the density of the vapor is 0.5977. And at this moment, the density of liquid will be 57.9 kilogram per cubic meter. You might say, well, Professor, something wrong. When I learned the density of water, which is about 1,000, right? If you talk about one density of liquid of the water, which is that will be gram per cubic centimeter. That will be 1,000 kilogram per cubic meter, right? So this is not exactly 1, but it's close to 1, right? Okay, let's remember this number here. And then the phase will be 2, because phase 1 is gas, phase 2 is liquid. Okay? Right, this is round 2. Let's talk about round 3. What happened to round 3? If I increase the temperature, let's make T1 become T2. Okay? Okay, T1, T2. Okay, let's T2 here, for example. Again, there's always gas phase H2O. Again, you have a piston, you push this down. And at this 200 Celsius, and then you find out if you push the piston down and the first drop of the liquid come out, please tell me the pressure will be higher than 1 or pressure will be lower than 1. Which one? You need to be pushed harder, or you don't need to push that much in order to get the first drop of liquid come out. Anyone? Of course, you need to push harder, right? Because the temperature represents kinetic energy. Kinetic energy of the liquid, of the gas, of the H2O is very active. They don't want to be too close. Because when you think of the first drop, that means you need to put the liquid H2O molecule very, very close. Right? So you need to push this harder. So the pressure will be high, very, very high. If you increase 2 times from 100 to 200, this increase 15 times. The pressure increased 15 times. And at this moment, when you measure the density of the vapor, increase. Why? Because this temperature, this is more. This pressure represents what? Density. Okay, so density of the vapor increase, and liquid, the density of liquid will be what? Decrease. Because they don't want to be too close. Okay, because high temperature. So as you can see, if you appear into 2 phases, then the density of the vapor will increase, the density of the liquid will decrease. Okay, this is round 3. What happens if you do the round 4? If you increase the temperature again, increase to 3 times, from 100 to 340 or 350. So the pressure increased dramatically from 15 to 163. And then again, the density of vapor increase, the density of liquid decrease, and it becomes 2 phases. You might say, well, Professor, I don't want to increase the temperature, I want to decrease the temperature. What happened? If I decrease the temperature to 25, imagine all the gas, this is temperature is 25, and this is in gas phase. And you started to push, piston push down to make this volume smaller. So the first drop condensed will be 0.0329 atm, which is you don't need to push too hard. The first drop will come out. And at this moment, the density of the vapor here will be very low. And the density of the water will be what? 1,000, which is 1 gram per cubic centimeter. It becomes 2 phases. So as you can see, if I increase the temperature, and then the density of vapor increase, the density of liquid decrease, the density of gas increase, right? Okay, so let's do it. Round 5, increase the temperature again, and you will see that this increase. Then, of course, the pressure increase, the density of vapor increase, density of liquid decrease. Okay, so as you can see, these two, the density of vapor and density of liquid is getting closer and closer. Right? Okay, when I go to round 6, when I go to the T1, which is 374.15, the pressure of condensation will be 218.3. At this moment, the density of vapor will be equal to the density of the liquid. At this moment, it's still 2 phases. So you might say, well, Professor, what happened if I go to round 7 and I increase the temperature to 400? So what happened? Will I have 2 phases? No. There's no way to have 2 phases. So if I increase temperature more than 374 and there's no condensation occurs, there's no liquid anymore. So only 1 phase. What kind of phase is this? We call this supercritical fluid. Okay? Okay, supercritical fluid. So this is kind of example to show you what's going on with the when you play temperature and pressure in a system, what's going on with this system. Eventually, if you increase the temperature, if this is a closed system and you increase the temperature more and more, then eventually you will make this fluid become supercritical fluid. Okay, so the definition of the critical temperature and critical pressure is that the critical temperature is the highest temperature that at which a species can coexist into two phases. Here is two phases. Okay, liquid and vapor. It's a critical temperature of this species. We use Tc. Okay, so what is critical pressure? So this is Tc here. So for water, Tc will be 374.15 Celsius. How about the pressure? The corresponding pressure is critical pressure. So this is the corresponding pressure, which is 218.3 atm. So this is the highest temperature and highest pressure to let the system with two phases. Okay. So let's go back to this table. So you understand this table, right? This critical temperature, this highest temperature and highest pressure to let carbon dioxide has two phases. Okay, if you increase the temperature more than 31.1, there's no, you cannot have one phase. You cannot have two phases. Only one phase, which is supercritical phase. Okay, or we don't call it supercritical phase. One phase, and that fluid is called supercritical fluid. So what is supercritical fluid? As you can see, these two phases coexist. This is liquid phase, this is gas phase. When you this is a closed system, and when you increase the temperature again, it will reach to what we call subcritical, which is very close to critical, but it's not. It's very close. And when you reach the temperature reach above supercritical condition, you will become supercritical fluids. Okay, so a substance at temperature Tc and Pc is said to be at its critical state. Okay, and in this state, the fluid is called supercritical fluid. So supercritical fluid, we use SCF, supercritical fluid. Okay, it's the substance at temperature above critical temperature, and the pressure above Pc are referred to as a supercritical fluid. So you must. So how are we going to define in this phase, in the phase diagram? This is the phase diagram for the carbon dioxide here. So as you know, this is a conventional phase diagram. In the x-axis is temperature, y-axis is pressure. So if you think of this, the circles, these kind of circles represent density. As you can see, the density of gas is lowest. The density of solid is the highest. So as you can see, the between is liquid, right? So as you can see, the distance between these circles is very far in the gas phase, and the distance between circles represent molecular or atoms are very close. So the density of the carbon dioxide in solid phase is greater than the density of the carbon dioxide in liquid phase, and then greater than the density of the carbon dioxide in gas phase. And as you can see, as you know that the the supercritical fluid state for the carbon dioxide is 31 here, okay, 31.1 here, and this part is 72.9 atm. So the temperature, this dashed line from x-axis and this dashed line from y-axis, this square is called supercritical fluid. The gas phase, liquid phase, solid phase, and supercritical fluid. And there's no dot here because it's very difficult to define this. What is this? I'm going to show you later. Okay, I'm going to show you what is exactly supercritical fluid. You know, carbon dioxide is a good example, a good experiment to do, because you know, carbon dioxide, the temperature of the critical temperature of the carbon dioxide is low. So we use this as an example. This is a video showing you that how supercritical fluid. Okay, what's the property of the supercritical fluid? The property is that, as you can see, at this moment, the density of liquid increase, right? The density of liquid increase from very low to very high. Okay, so liquid here, so you have very high density of liquid. And the viscosity and diffusion as a gas. So even this is in the liquid state, but the diffusion means what? How fast this molecule can move, right? It can move very fast. Viscosity means what? Friction. The friction is very low, like gas. So this kind of fluid has a good part of the liquid, has a good part of the gas. So this is very good. So that's why we call super, right? Supercritical. So this molecule can move very fast without any friction, without any energy exchange, or without any energy loss. But the density is very high, so a huge amount of molecules and working together. Okay, if you regard a molecule as a kind of reactant, okay, so you have a lot of reactant, and they are active very well. Okay, so excellent dissolving abilities, especially this carbon dioxide. Carbon dioxide is a kind of environmental friendly chemical. Or you can use water. Okay, of course, water needs to be in very high temperature and high pressure. So for the application of the supercritical fluid, because we know that this can act like a solvent. So it can dissolve things very quick, very well, and very quick. For example, like decaffeination of coffee and tea. So you don't want coffee with caffeine. You can use supercritical fluid to remove caffeine. That's what we call decaffeination, right? Or if you have tobacco, if you smoke, and you don't want to have nicotine so much, so you can use supercritical fluid to nicotine it. Okay, so if you go to the 7-Eleven, you buy tobacco or cigarette, you can have different level of the nicotine, right? You can have different level of the nicotine. Of course, you can use this for cleaning, especially if you want to eat rice. Remove there's no any contamination. You can remove heavy metal from the rice. Of course, there's kind of purification of contaminate soil. There's kind of heavy metal contaminate oil soil. You can use this kind of supercritical fluid to remove some heavy metals from the soil. So you can see this in the market. They use supercritical fluid carbon dioxide technology to make the rice more healthy. I don't know if it's more healthy or not, but you remove some of the unnecessary things away from the rice, right? Okay, so this is technology. Right. So now you know what is supercritical temperature, supercritical pressure, and supercritical fluid. So there is one thing I want you to know is that when we talk about vapor or gas, what's the definition of vapor or gas? So let's use H2O as an example. H2O in liquid phase, we call it water, right? What's happened? If it's in gas phase? What do we call it? Steam, right? Or gas, vapor or gas. Steam is what? 水蒸气, right? But what's the 水气体? Okay, have you heard about that? Okay, that means how are I going to define vapor or gas? So this is one. We define this by the critical temperature. If the gas is a species above its critical temperature (Tc) at a pressure low enough, that means it's not too high. The pressure is not too high. So we use gas to represent this species. However, if the temperature is lower than critical temperature, we use vapor. to represent this species. So let me give you an example. So the critical temperature and pressure of the isopropanol 异丙醇 are Tc equal to Tc is 508.8 Kelvin and Pc is 53 atm. So if isopropanol is in a gas state at T equal to 400 Kelvin, so T is 400, right? The supercritical critical temperature is 500, okay? And 1 atm, 1 atm, which is relatively low enough, right? Lower than the 53. Will it be classified as a vapor or gas? Which one? So at this moment, isopropanol will be called vapor, or isopropanol will be called gas. Which one? Vapor, right? Vapor. Because the temperature is 400 is lower than 508. Okay? This is a simple definition. Right, so now we are going to introduce you equations. You know that if this is ideal gas, we use PV equal to nRT. However, there's nothing real, there's nothing ideal. So we need to modify PV equal to nRT. The first equation we want to introduce to you is called Fourier equation of state. But before we really go into this topic, let's refresh ourselves. So now, let's use mathematics to represent the non-ideal gas equation of state. The first equation I want to introduce to you is Fourier equation of state. So as you know, this is ideal gas equation of state, which is P times V over carat. What is V over carat? It's volume divided by what? Mole, right? Mole, okay? So this is called specific molar volume divided by RT, gas constant times temperature equal to 1. This is ideal equation of state. But we are talking about non-ideal equation of state. So that's why we need to have small terms in this case. So we have 1 plus B divided by V over carat plus C divided by V over carat power 2 plus blah 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 3, 4, 5. So this is a Fourier equation of state. So what is B, C, D? B, C, D, E, F, G are second, third, fourth coefficient, are a function of the temperature. Okay, so V, this is volume, right? Specific molar volume, and B is related to the temperature. So basically, pressure here, and you modify volume and you modify the temperature. Okay. So for a single species, this V over carat we call specific molar volume. Okay, which is V divided by N, right? The second one, the Fourier equation has a theoretical base in the statistical mechanics. So from B, this is a theoretical basis. There's some meaning of B, but not others. But C, D is kind of empirical coefficient. Empirical coefficient means that you do experiment and you get the answer and you try to change C and D to make it become the data you get from the experiment. Okay, this is called empirical coefficient. But B has a kind of theoretical basis. I'm going to show you what is B. So if B, C, D equal to 0, that means this one 0, this term will become 0, this term will become 0, and also this term becomes 0. This will be ideal equation of state, right? Okay, so let's talk about the Fourier equation here. So if we're truncating C, D, E, F, that will become what? That will become, we call truncated Fourier equation of state. This is truncated Fourier equation of state. C, D here, you remove this. Okay, so this is Fourier equation of state This is truncated variable equation of state. Okay? So variable equation of state used in what? Normally, this equation can be used in a non-polar species. For example, like hydrogen, or like oxygen, okay? Or nitrogen, for example. There's non-polar species. For the polar species like oxygen, like water, this is polar component. So this is not suitable for variable equation of state. So how to get B? It's important, right? Because you know the relationship of the pressure, volume, and temperature, and now you have a one coefficient here. So how do you estimate B using B equal to this? So B is R times Tc divided by Pc times B0 plus omega B1. You don't need to remember this equation, okay? If this is in your final exam paper, I'm going to show you this equation. But I don't want to tell you what is Tc, what is Pc. Please tell me what is Tc, what is Pc. Critical temperature and critical pressure, right? So if we use this as a to estimate the nitrogen gas, or for the measurement of oxygen gas, nitrogen gas, you need to know the critical temperature and critical pressure of nitrogen or oxygen by checking the table. Excuse me. Okay? But I will tell you why. You might say, well, Professor, why is B0 and omega, why is B1? I'm going to tell you now. B0 is 0.083 minus 0.422 divided by TR 1.6. So please bring your calculator when you have your final exam. Okay, so again, you don't need to remember this, but I don't want to tell you what is TR. You need to remember what is TR. What is TR? Okay, B0 is this one, and B1 is this one. So what is TR? TR is what we call reduced temperature. This is a dimensionless quantity. Reduced temperature means what? The temperature divided by Tc. You know what is Tc? Tc is critical temperature, right? So TR is reduced temperature, which is T, the temperature divided by critical temperature. If we use nitrogen, that will be nitrogen's critical temperature of nitrogen divided by, that will be temperature of nitrogen divided by critical temperature of the nitrogen. Okay, so I don't want to tell you what is TR. You need to know what is TR, a definition of the TR. And this is a dimensionless quantity, right? Dimensionless quantity. And so now there's only one remain, which we don't know. You know B0 is here, B1 is here, and B0 you have a TR. You know TR is here. So what is there's only one unknown here. It's called omega. Omega. What is omega? Omega is because this is for the non-species, non-polar species. So non-polar species is how far is away from the non-polar species. That's what we call pizza eccentric factor, omega. Pizza eccentric factor. So what is pizza eccentric factor? A parameter that reflects a geometry and polarity of a molecule. Polarity, right? Because we want non-polar species. So next page, I want to show you eccentric factor, pizza eccentric factor. So this means omega, if omega is close to 0, that means it's non-polar. Here I want to show you argon is a non-polar species. So the omega is almost 0. Okay? And methane, which is non-polar molecular, is almost 0. But water, H2O, so oxygen, again, the same. Nitrogen, carbon monoxide, right? As you can see that carbon monoxide is increased because carbon monoxide is non-polar molecular. Carbon monoxide is polar molecular. Increase. And one which is very high is water, because quarks has what? Water is non-polar molecular, right? And if you have two molecules together, that will have hydrogen bond. Not good, right? Not good. It not tend to become ideal gas. It tend to become liquid. And also methanol, right? You have an OH over there in the methanol. Okay, so as you can see, we can, if we have omega, we can use omega. In your final exam, if I won't ask you to remember omega here. I will give you a table like this. So this is the example 5.3-1, a truncated Virial equation. This is truncated Virial equation. Again, I don't want you to remember this equation. I will give it this equation to you if you have this in your final exam. So ideal gas equation is that, for example, this is 5.3-1. Let's say that. Oh, let's see what is this. On page. Okay, so please work with me and on the page 175. Example 5.3-1. Right. So are you with me? Are you with me? No? Yes? Okay, anyway. 2 grams moles of the nitrogen is placed in a 3-liter tank at minus 150.8 Celsius. So you have 2 gram mole of nitrogen. And then you have 3-liter tank. And temperature is minus 150.8. So as you can see, temperature is quite low. So it's not easy. Minus 150 is not high. Is not above 0 Celsius, right? So when we talk about ideal gas, normally is above 0 Celsius, but this is minus 150 Celsius. It's too far from the ideal, right? So you might say, wow, maybe this is not a good idea to use PV equal to nRT, right? Right, so estimate the tank pressure using the ideal gas equational state, and then use the Virial equational state truncated after the second term, taking the second estimate to be correct. Calculate the percentage error that result from the use of the ideal equation at the system condition. So the textbook tell you that assume the truncated equation, the truncated Virial equational state can be applied in this case. So he want to ask you the error, the percentage error, of which is what? Epsilon, right? Epsilon. We just have Kahoot. Remember epsilon? Epsilon, the absolute value of epsilon need to be less than 1. That will be regarded as an ideal gas. So we want to see, in this case, the absolute value of the epsilon will be less than 1 or not. Okay? So let's see that let's take a look of the slide here. So if we use, we have temperature, we have volume, right? And we have B here. You know all the parameters already. So when you do the calculation, this is ideal equational state. So P ideal times V over Kara equal to RT. So when you do the calculation, the P ideal will be equal to 6.73 ATM. Please do this by yourself. I don't want to waste your time. So truncated Virial equational state is that B, you just use your calculator, okay? Just so you can do it like this. B is this. So you can put this B, you can get this answer here, and eventually you got the pressure will be 6.19. So the example tell you that assume this is correct. So you want to see epsilon, the percentage error. What is percentage error? So epsilon is that P ideal divided by P, this one, minus P divided by P words, which is 8.7%. And this is greater than 1%. So obviously, ideal gas equation of state cannot use in this case. Right? Right. So this is easy, as long as you know the equation, right? And you just do the calculation. So another equation is called Benedict-Webb-Robin, we call BWR equation. Again, this is, there are many equations. We don't want to introduce you all the equations because there are some minor change only. So there's 8 empirical constants for light hydrocarbon and the nonpolar gases. Okay, so you can check this in the Paris Chemical Engineers Handbook. Right. So let me summarize sorry, I don't want to summarize this. Please read this, and we do a recap next on Wednesday for this. So the second equation I want to introduce you is called cubic equation of state. Cubic equation of state. What is cubic equation of state? So this is ideal equation of state. This is variable equation of state. This is truncated variable equation of state. Right? So as you can see, you modify the value and temperature here. So as you can see here, here is that what is cubic equation of state? Cubic equation of state is that this equation is a function of the cubic volume. Okay, which is value power 3. It's called cubic equation of state. So for single species, the equation, there are many equations related to, which is a function of the cubic volume. So there are van der Waals equation of state, and Radix-1 equation of state, and Soviet-Radix-1 we call SRK equation of state, or Penn-Robinson equation of state. There are many equations related to this cubic volume. And today, this book, we only introduce you this one, van der Waals equation of state and the SRK equation of state. Right, so what is van der Waals equation of state? This is called van der Waals equation of state. Again, I don't want you to remember this equation. But you need to know what is V over caret, right? What is A, what is B? I'm going to show you what is A, what is B. So when you think of this, you might say, well, Professor, what is this related to cubic volume? This is cubic volume, right? V power 1, V power 2. Okay, so this is cubic volume. So they have some physical meaning here. So when you have B, B means what? B is a correction accounting for the value occupied by the molecules themselves. So as you can see here, the value minus some portion means what? This value will reduce in the system. Okay, this value will reduce in the system. Why the value will reduce in the system? Because molecules occupy some spaces in the system. So the value is not as you expected, as big as you expected. It's smaller. So you have B here. And when you see this term, is that the P is this one and minus some portion. And why the pressure will be less than you expected. Why? Because molecule has attraction. Because this is against ideal equation, right? This is against the ideal gas. Because all molecules has attraction force. So attraction force between molecules. So the pressure has to, this is pressure, minus some portions means that the pressure is not as big as you expected. It's smaller than you expected. So this is the van der Waals equation of state. And now the question is, what is A and B? A is this, B is this. So now you understand R is gas constant. What is TC? What is PC? Critical temperature and critical pressure of, in this case, it can be nitrogen, it can be oxygen, right? It can be methane. Okay, again, please, you don't need to remember this. I will give you this when you do your calculation. Okay, so this is van der Waals equation of state. So what you need is TC and PC. This equation is easier compared to variable equation of state, right? Because van der Waals equation of state, you only need A and B coefficient. And what you need to find out is the critical temperature and critical pressure. And you input this temperature and pressure into this equation, you can get an answer. So you can have, if I give you pressure and temperature, you can get value. Okay, if I give you temperature, I give you volume, you can get pressure. Right? Because these are all constant. Right? R, B, A are all constant. So variable equation of state like this. How about SRK equation of state? So this is SRK. As you can see, this is slightly modified the van der Waals equation of state. Again, please don't remember this. I also gave you this. So this is van der Waals. As you can see, the first term is the same, but the second term was modified by van der Waals equation of state. So here we have another parameter called alpha. So 5 parameters. They are A, B, alpha, right? And when you have alpha, this alpha is M, TR. Do you still remember what is TR? Reduced temperature, right? Reduced temperature. M is what? M is this. So you might say, wow, Professor, trouble is keep on coming. No trouble. I will give you all of this. So you know what is M? I don't want to tell you what is omega. Please tell me what is omega. Pizza eccentric factor, right? Just check the table. TR, you know, is T minus TC. So there are 5 parameters, A, B, alpha, M, and TR. Right, so this is SRK equation of state. So again, as you can see, these are all called cubic equation of state, right? Because this is value power 3. This is value power 3. Right? This is a cubic equation. Right? Cubic equation. So this is an example. This is SRK equation of state. We use carbon dioxide as an example. And value is 2.5 cubic meter. Is 1 kilomole. And temperature is 300 Kelvin. What is pressure? Easy, right? So if this is SRK equation of state, and I tell you volume, right, and mole, right, so you can get specific volume, and I give you the temperature, so you can get the answer of this, you can get the answer of this, answer of this, answer of this. This is constant. Alpha, you can get this, right? And M, you can check it from the table. Carbon dioxide, you can have omega, right? So these are all constants. So the important thing is you have temperature, you have volume, so you can get pressure. Easy. What happens if I give you pressure and temperature? You can get volume. But this is cubic equation. Can you get cubic answer of a cubic equation? 一元三次方, right? Can you get the answer? Yes, you can. Right, so I don't want to waste your time. Please go home and practice this by yourself. So because I give you volume, I give you the temperature, you can find out pressure using ideal equation of state. Right, so you can get ideal, and you can also measure the pressure. So you can compare these 3. Okay, so this is another example. Another example is the estimated volume using the SRK equation of state. Again, if I give you the temperature, if I give you the pressure, can you give me the volume? So the temperature is 423 Kelvin. The pressure is 0.7. It can be 7, it can be 70. And can you find out the specific volume for me? Or volumetric flow rate? So what is 一元三次方? What's cubic equation? What's the answer of cubic equation? There's 3. If this equation can be solved, so there are 3 answers. Right? There are 3 answers because this is a cubic equation. 3 answers. So which one is the best? Which one is the right answer? 一元三次方如果有解的话是得到3个解，对不对？没错吧？那 which one is the best? Or which one is the correct answer? The one close to ideal equation of state, right? It cannot be too far from the pressure you get from the value you get from using ideal equation of state, right? Okay, let me give you this example. So I give you the pressure, I give you the temperature. You need to find out the volume. It takes time, but it's fun, right? It's fun. You are happy to do this. It's a cubic function. So how do you get a cubic function? Normally, if you go to second year, the Professor Chen will teach you how to do this in doing trial and error or doing mathematical method. Okay, so the important thing is how are you going to find out the initial volume from this cubic function? As I just told you, initial volume will be the one you use, the ideal equation of state you use. Okay, so the volume here. And you use minus plus to increase the volume or decrease the volume to get the answer which is close to the true answer. Okay, so you get the function of volume. So let me show you an example. This is called cubic function. For example, this is y equal to x power 3 minus ax2 plus x plus 15. So as you know that if you draw this equation in this plot, you will get something like this. And what you know is that if y equal to 0, you can get 3 answers. Right? X will get 3 answers. What is x in this case? X is volume. Y is what? P, right? Y is P. Right, so this is V over K, right? This is A here. I'm sorry, Y is not P. If Y is here, you go to the Y here. And then this is a cubic function. So you get 3 answers. So you get the first point. How can you get the first point? So the answer, the real answer is that this is the function of V answer is going to 0, right? Okay, 0 here. So you have V1, A1. V1, A1 is what? This is the true answer. And you start from the beginning using V1, A1. What is V1? V1 is ideal. You use PV equal to nRT, you got V1. And you got A1 here, is A, V1, A1. And then after that, you understand V1, A1, you got here is that the function of V1 is equal to A1, and which is less than 0. And you need to find out A2, which is greater than 0. So you find another V, you try to find V2. V2 is, and V2, you got A2. So A2 need to greater than 0. The next one, you need to find out, you need to go to here or go to here. Between what? Between V2, V1 and V2, you need to pick one. Pick up one. For example, you pick up V3, it can be greater, so V2, for example, you can have V2, V2 is larger than V3, larger than V1. So as you go this, you can go into this end. You can get the answer close to this point. It's what we call try and error. But you know, if you know how to do the computation, you need to, if you know how to write a code using computer, this is easier, right? This is easier. That's why you need to know how to write down, how to write this, how to write code. But probably now you ask Ch5.3 to get this answer for you. Ch5.3 can write GPT can write code for you, right? Right. So this is how you get the answer. So as you can see that, but you can also use Excel to do something like this. Okay. So the example I want to show you is that according to this cubic function or the SRK equation of state, I give you pressure and temperature, you can get volume. I give you the temperature of volume, you can get pressure. So you are playing these three factors: pressure, temperature, and volume. Okay? Right. So this is summary. I think I better stop here. Right. Okay.